Okay, so in this video we want to take a pause from looking at our graphs of sine and cosine, although you'll see there's a graph pictured here because intrinsically solving a equation and considering that in a graphical way are very closely connected. But we want to take a pause from the actual kind of sketching of the graphs while we learn how to solve equations involving circular functions, so trigonometric equations. And we need to do this before we begin to add in our final transformation with our graphs, which is to start to translate them up and down. Because once we begin to translate them up and down, we're no longer going to be able to simply rely on good scaling of the x-axis in order to draw the graph, in order to find the x-intercepts. There will be a need to solve an equation to find the x-intercepts. So before we get to that point, we obviously need to learn how to solve equations. So I'm going to do this over two videos. The first will be solving very, very simple trig equations where there's not too much going on. And then there'll be a second video to follow this one, looking at more complex equations where there is a bit more going on within the sine or the cosine function. Okay, so what I want to think about is, I do want to start by thinking about the fact that anytime we solve an equation, we can always think about that graphically. So, for example, if we consider this equation here, sine of x equals 1/2, that can be thought of as the points of intersection where the graph of y equals sine of x, which is the blue graph, intersects with the graph of y equals 1/2. That's what we're doing when we're solving sine of x equals 1/2. We're finding the points of intersection, or the x values of those points of intersection, where those graphs intersect. So for example, this x value here, whatever it might be, that's a solution to that equation. This x value right here, that's another solution. This x value here is another solution. This one's another solution, etc. So what we want to note first of all when we're solving trig equations is that because the trig function, in this case y equals sine x, has a domain of R, if it's not being restricted, its implied domain is R, and it's a periodic function, there will be infinitely many solutions to this equation, sine of x equals 1/2. So, you know, I've highlighted 6 there. We can see a 7th one up here. We can see a further 1, 2, 3, 4, 5, 6 back here. But we can certainly note that that would continue, okay? So there are infinitely many solutions to the equation sine of x equals 1/2. And that's why I'm just going to show you on the CAS over here, just checking I'm in radian mode, which I am. So if I want to, let's solve first, menu 3.1, sine of x equals 1/2. For x, my CAS will give me this, okay? And this is not broken. It's actually completely accurate, and this is what we call the general solution to the trig equation. This is giving us a way to find every single solution to this particular equation. Now, we don't look at general solutions in Year 11. In Year 12, we will look at how to determine the general solution to a trig equation by hand. But what we're interested in is just some of the solutions. So say, for example, if we just wanted the solutions between -6 pi and 6 pi, then that would be these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 solutions that I've identified here. That extra one I had labelled over here, that's past 6 pi, so not within that domain. If we just wanted the solutions to this equation between 0 and 2 pi, there would just be 2 solutions, these 2 values here, whatever those 2 x values are. Okay. If you want your CAS to give you those solutions, you would need to tell it about the domain, okay? That you want to solve that trig equation, but only, for example, where x is between 0 and 2 pi. If we want to do that, I'm going to talk about this now. We want to go on and look at how to do this by hand, obviously. But if we want to solve the equation and actually get specific solutions, not the general solution, we must give it a domain. So anytime the equation involves a circular function, and you may have seen this previously, I certainly discuss it with my Year 10 class when we start to look at sine rule and cosine rule in first semester of Year 10. When we're solving equations there's a need to include a domain restriction. Now, if you want to restrict the domain for an equation, you cannot interfere with the syntax of the solve function. So solve, bracket, equation, comma, x bracket. We can't change anything about that. You can't put anything else inside that bracket. This is the most common mistake students make. They try to put their domain restriction inside the solve function. So solve, just as usual, nothing changes about solve, close the bracket to the solve function. After that, we want to say, given that, so control equals, given that, and let's say 0 to 2 pi. So 0 is less than or equal to, so the inequality symbols are in control equals as well, x, which is less than or equal to 2 pi. It is quite tedious to enter in the domain restriction, but it's the only way to get it to give us exact solutions. And now when we press enter, it will just give us the two solutions that we can see on our graph here that are happening between 0 and 2 pi. And in this case they are pi on 6, which is that one, and 5 pi on 6, which is that one, which seems to marry with what we're seeing on the graph. Okay. Now, I want to have a look at how we're going to be able to actually get those solutions by hand. But the important thing is to understand when using your CAS, if you don't want the general solution, when you get the general solution, your CAS isn't broken. It's just telling you there are infinitely many solutions, okay? And therefore you need to be more precise about what you want it to do, and you need to give it the domain restriction. Okay, let's sort of talk through. I've got 4 steps which are the process for solving a trig equation, and it'll be these same 4 steps when we look at the next video on more complex trig equations. The only thing that makes them more complex is we're going to have to do a lot more thinking at this moment, and I guess there's probably a 5th slightly loose step, which is pretty obvious once we've dealt with step 4 more sufficiently. So this is where a lot of our understanding of our trig functions is going to come together. All those little bits that we learned at the beginning about the symmetries, your exact values, the basic definitions of sine, cos and tan are all going to come into this. So I've tried to structure it into some steps. The first thing is to rearrange the equation, so the only thing on the left hand side is sine of something or cos of something or tan of something if it's a tan equation. We'll revisit those. We'll look separately at the tan function down the track. Then once we've done that, we then need to use our exact values to determine what I'm going to call the reference angle. Okay, so this value won't necessarily be a solution to the equation, but all of the solutions will be connected to this value. Okay. Then we need to work out which quadrants our solutions will be in. This is to do with our cast rule, or having an understanding of when sine and cos are negative, sine being the y-coordinate. Y-coordinates are, sine or cos are positive or negative depending on what your equation requires. So whether, sine is the y-coordinate, so it's positive in the first and second quadrants, and it's negative in the third and fourth. Cos is the x-coordinate, so it's positive in the first and fourth quadrants, negative in the second and third. And then we need to use our domain. We're going to be working from the unit circle. So what we're trying to work out in the first 3 steps, well, steps 2 and 3 really, where in the unit circle are my solutions located? And then step 4 is about, okay, how many laps of the unit circle do I need to now do given the domain that I'm dealing with? Okay, let's talk that through here. So example 1 is what we're seeing in the graph. We've actually already got our CAS to solve this for us, so we know what solutions we should be getting. So what we're looking at here is solving the equation y equals sine of x, but only between 0 and 2 pi. So only interested in this bit here. Okay, forget about the rest of it. So we know there should be 2 solutions. We know from our CAS they should be pi on 6 and 5 pi on 6. So let's pretend we haven't solved it already though. Okay, so step 1 is to rearrange the equation so it's in the form sine of something equals something, or cos of something equals something. So it should be nothing other than sine of something on the left hand side, and that's how we've already got it. So what that first step is about is I could give you this exact same equation as 2 times sine of x equals 1, and the first thing you would need to do would be divide both sides by 2 so that you just have the sine on its own on the left hand side. Okay. In this case that's already done. So sine of x equals half. Then we need to use our exact values to determine the reference angle. Now, as I said, this isn't necessarily a solution to the equation, but every single solution will be connected to this reference angle. So what we're looking at here is sine of x is equal to 1/2. Okay, so we need to know our exact values, or as I've advocated before, we need to know our special triangles so we can generate our exact values. And we want to think about, well, if sine of x has to be equal to 1/2, that means I would need 1 to be the opposite and 2 to be the hypotenuse, so that sine opposite over hypotenuse is 1/2, and therefore I must be talking about this angle up the top here. and that angle is pi on 6. So in this case, pi on 6 is my reference angle. All my solutions are going to be connected to pi on 6. That doesn't necessarily mean that pi on 6 is a solution to the equation. In this case it is, but it doesn't always mean that. Because the next thing we need to think about is, okay, my solutions are all about pi on 6, connected to pi on 6, but which quadrants are they in? Okay, so in this case, now what we're looking at here is sine is equal to positive 1/2. Okay, so sine is equal to positive 1/2. Let's think about our unit circle and what that means. So we know that sine is the y-coordinate. Okay, so where is the y-coordinate 1/2? All right, well there's where the y-coordinate's 1/2 in the first and second quadrants. So there are two locations in the unit circle, one over here and one up here, where the sine value is equal to 1/2. And we know from what we've just calculated in our triangle, from our exact values, that that angle there is going to be pi on 6. Okay, and therefore this angle in here is going to be pi on 6. Okay, so we now know the location of our solutions. Okay, the next thing we need to think about, I'm running out of colours because I got overexcited with colours at the beginning. So the next thing we need to think about is, so we've done the first two steps, first three steps. We've rearranged, which we didn't need to do. We've used our exact values to determine our reference angle, which was pi on 6. We've determined which quadrants our solutions are in. So now we know they're solutions to do with pi on 6 in the first and second quadrants. So those pink lines are giving me the location of all the solutions. Then we need to use our domain to find the required solutions. So in this case, our domain is 0 to 2 pi. So in our unit circle, this is 0 here. 2 pi is one full lap around the unit circle. That's 2 pi there. That's pi over there. Okay. So we're traveling around the unit circle, and we can see that when we look between 0 and 2 pi, there are two solutions. Okay. This one here that's at pi on 6 in the first quadrant, and this one around here in the second quadrant, which will be at pi minus pi on 6. So our solutions, x is going to be equal to pi on 6, or pi minus pi on 6. I'll write that line out, but you don't need to write it out if you can do that in your head. And so x is equal to pi on 6, or 5 pi on 6. So this question is asking me, which angles give me a sine value of 1/2? Which angles make the y-coordinate in the unit circle equal to 1/2? Now there are infinitely many answers to that because we can spin around the unit circle infinitely many times, and we can, we could do another lap and say 13 pi on 6 and what will it be? 17 pi on 6. They're also solutions, but they're not within this domain. Okay, we could also have gone around the negative. We could have said, oh, well, it's negative 7 pi on 6 and negative 11 pi on 6, but they're not in this domain. Okay, so we only want the solutions that are between 0 and 2 pi, which will be 0 plus pi on 6 and pi minus pi on 6. Okay. Example 2 is exactly the same equation except with a different domain. So all the information we've done for steps 1, 2 and 3 apply. So my identifying pi on 6 as my reference angle, finding the location of the solutions in the unit circle is all still correct for this equation. But the difference is we're going to do 2 laps of the unit circle. So this time, let me draw, I should have drawn my circle first. So let me just draw myself a new diagram. Just make my circle a bit smaller. Let's draw myself a new diagram so I can see what's happening. Okay, once again, we know our solutions are in the first and second quadrant, pi on 6 up from the x-axis. This time we want all the solutions between negative 4 pi and 4 pi. Now personally, I find it much easier to, rather than to count from negative 4 pi all the way up to 4 pi, I find it much easier logically to work in the unit circle if I work from 0 around to positive 4 pi, and then I find the positive solutions, and then I go back and I work from 0 around to negative 4 pi. Okay, it's easier to be going, because you have to go in 2 different directions around the unit circle, it's easier to do it that way, in my opinion. Okay, so let's focus first of all on the positive solutions. So again, we want to go from 0 to 4 pi. We're going to start at 0. We're going to do 1 lap around the circle. This is pi. 1 full lap takes us around to 2 pi. We need to go to 4 pi. Second lap. This is 3 pi around here. fourth lap takes us around to 4 pi around here. Okay, so what we're seeing in terms of positive solutions, we've got to go back and do the negative ones, that we have 1, 2, 3, 4 positive solutions. Okay, so I'm going to start by writing them out. So these are the equal to x. Okay, these are what angle gives us a sine value of 1/2. So x will be equal to, now we're going to have 4 positive solutions. Our first one is 0 plus pi on 6. So that's just pi on 6. Our next solution is in the second quadrant. It is pi minus pi on 6. That's 5 pi on 6. We had those two solutions already. They're the two solutions between 0 and 2 pi. But we're doing another lap. So my next solution is back around in the first quadrant, 2 pi plus pi on 6. So 2 pi is 12 pi on 6. So therefore 12 pi on 6 plus another pi on 6 is 13 pi on 6. Okay, and around again into the second quadrant there's another solution which is at the location of 3 pi minus pi on 6. Now 3 pi is 18 pi on 6, so 18 pi on 6 minus pi on 6 is 17 pi on 6. Okay, so that's the 4 positive solutions. We're also going to have 4 negative solutions. So I'm going to erase my annotations there as much as I can without erasing all the important stuff. Oh, like that. Okay, so, sorry. Struggling. Okay. Got it. Okay, so this time we're going to go the other way. So this time we're going to be starting at 0, but we're going to go into the negative direction, so we're going to head out this way. Okay, so this is 0 here. We're going to go around. This is negative pi here. We're going to keep going around. This is negative 2 pi here. Around again. That's negative 3 pi. And then finally around to finish at negative 4 pi. Okay, so what we see in that process is that we again have 4 solutions. 1, 2, 3, and 4 solutions. Okay, 2 in the first quadrant, 2 in the second quadrant. Okay, so again now we want to work out what the value of those solutions are. So I might write my negative ones on the next line. So we're travelling clockwise around from 0. So passing through the fourth quadrant, passing through the third quadrant, then we're back. Our first solution is back here. So it's at minus pi minus another pi on 6. Okay, so minus pi is negative 6 pi on 6, minus another pi on 6 is negative 7 pi on 6. Okay, continuing around again. So now we continue, we're now around to the one in the first quadrant here, which we can think of as being negative 2 pi plus pi on 6. So remember, going in an anti-clockwise direction is positive, going in a clockwise direction is negative. So if we're at negative 2 pi and we want to come back up here to this solution, we're actually adding pi on 6 onto that. So negative 2 pi would be negative 12 pi on 6, plus 1 pi on 6 would be negative 11 pi on 6. Okay. Continuing more further around from negative 2 pi, so travelling around towards negative 3 pi, a little bit further, just another pi on 6 further, and we get to our next solution. So negative 3 pi minus pi on 6, so negative 3 pi being negative 18 pi on 6, minus another pi on 6 is negative 19 pi on 6. And our final solution rounded back in the first quadrant, so continuing around from negative 3 pi towards negative 4 pi, it's at negative 4 pi plus pi on 6. Negative 4 pi is negative 24 pi on 6, and then plus pi on 6 will be negative 23 pi on 6. Now I would say conventionally I'd write them in order from smallest to largest, so negative 23 pi on 6, negative 19 pi on 6, negative 11 pi on 6, negative 7 pi on 6, pi on 6, 5 pi on 6, 13 pi on 6, and 17 pi on 6. The other thing to note here is the reason we're getting repeat solutions is because of the periodic nature of the function. So let me just scroll back up here to the graph and let us think about it. So when we solved this, say for example between, let's just go with 0 and 4 pi, okay, we already knew from the first question that the first two solutions were pi on 6 and 5 pi on 6. Okay. Now we know the next solution is happening because we've hit the next period. So to get from this first solution in the first period to the first solution in the second period, we're just adding on the period. So in this case, the period is pi on 2. Is 2 pi. So pi on 6 plus 2 pi, pi on 6 plus 12 pi on 6, that gives me 13 pi on 6. This solution here is just the solution in the first quadrant plus a period. So 5 pi on 6 plus 12 pi on 6, which is 2 pi, gives me 17 pi on 6. So that's where those next two solutions come from. And then we can add a period again. Add a period again to get to the next pair if we need to. Okay, so you can also think about it in that way, and that's the same way you can also see that in the unit circle. So say, for example, here, the difference between these two values in what is just a whole other lap of the circle. So we're just adding on another 2 pi to go from one solution to the next solution. So what you should see is, so if I list them in order, okay, we'll list them out, just so I can make this point. Minus 23 pi on 6, minus 19 pi on 6, minus 11 pi on 6, minus 7 pi on 6, pi on 6, 5 pi on 6, 13 pi on 6, and 17 pi on 6. So what we see is they're the two solutions that were in sort of the one lap of the circle, 0 to 2 pi. Okay, every other solution is connected to this because they're all just one period away from this. So if we think about the pi on 6 solution, if we add 2 pi onto that, that gets us to 13 pi on 6. 2 pi in this case is the period of this function. Okay, it's 1x. If we then subtract 2 pi, we get to that solution. We subtract another 2 pi, we get to that solution. Okay. Equivalently, this was my other solution in one lap of the unit circle. Adding on 2 pi is going to get me to that next solution. Subtracting 2 pi will get me back to that solution. Subtracting 2 pi will get me back to that solution. Okay, so each solution should be just 2 pi away. So once you've established the two solutions in one lap of the unit circle, every other solution will just be 2 pi away from those solutions. But personally, I find it simpler to just continue to track my way around the circle until I've got all the solutions that I need. In this case, 8 solutions, because we are ultimately doing 4 laps of the circle, 2 positive laps and 2 negative laps. Okay, let's move away from sine of x equals a half and build in some of those earlier steps in a bit more detail. So solve cos of x equals 1 on root 2. So remember, our first step is to make sure the cos part of the equation's on its own, which it is. Okay, so we already have cos of x is 1 on root 2. The next part is to identify the reference angle. So this is where we look at, okay, cos of an angle is equal to 1 on root 2. What is an angle that would be true for? So this is where you've got to know your exact values or be able to reference your special triangles. So in this instance, I know that root 2 only happens in this special triangle, and so therefore it must involve here. And I know obviously there's 2 different ways we could look at this particular triangle, but if we think about, you know, this as being the adjacent side and this as being the hypotenuse, that would mean we're talking about this angle in here, and that is pi on 4. We could also have called this one the adjacent. This is also pi on 4 up here. Okay, regardless of which way you look at it, cos of pi on 4 is equal to 1 on root 2. Now that might be a solution, and it is in this particular case, but it won't necessarily be a solution. Hopefully there'll be an example down the track where we'll see that value itself won't be a solution. But what we do know now is all our solutions are related to pi on 4 in this equation. The next thing is to think about quadrants. In this particular question, cos of x is equal to positive 1 on root 2. So we're looking at where x, sorry, I'm confusing with the x orders, but where if the cos value is positive in the unit circle, that means my solutions are in the first and fourth quadrants. So we've got angles to do with pi on 4 in the first and the fourth quadrants. So pi on 4 up from the x-axis that way, and pi on 4 down from the x-axis that way. That's the location of every single solution to this particular equation. And there's infinitely many of those because we can lap and lap and lap and lap around the circle. Okay. Now what we want to think about is, well, specifically in this instance, how many laps of the circle do we want to do? So now we want to think about, okay, I've got my domain is 0 to 4 pi. So that is 2 positive laps of the circle. I'm going to start at 0. I'm going to lap around, that will be pi. Lapping around again, this is 2 pi. Around again. So let me try that again, got a bit. Around again to 3 pi. And finally back to 4 pi. So it's 2 full laps of the unit circle, which means we will cross our solutions twice. Well, each of them twice. So the first solution will be at 0 plus pi on 4. The next solution round in the fourth quadrant will be at 2 pi minus pi on 4. The next solution will be at 2 pi plus pi on 4 in the first quadrant. And the final solution will be around at 4 pi minus pi on 4. Okay, so 4 solutions to this equation. Oh, sorry. 4 solutions to the equation. Okay, so those 4 solutions are, okay, and each of those are values that if we stick them in here will make this equation true. Okay, that's the point of an equation, solving an equation. You're finding the values that make the equation true. There are infinitely many values that make this equation true. We want to know which ones of those between 0 and 4 pi. So in this instance, as I said, our 4 solutions, 0 plus pi on 4, so that's just pi on 4. Sorry, pi on 4. Our second solution in the fourth quadrant, 2 pi minus pi on 4. Now 2 pi is 8 pi on 4. Take away 1 pi on 4 is 7 pi on 4. This is where you need to get good with your fraction work, okay? So if that fraction work is hard for you to do in your head, this is going to be really challenging. It's really important that you work on being able to do those fraction calculations. We could write them all out, you know, you could write out, okay, I want to do 2 pi minus pi on 4, so that is 8 pi on 4 minus 1 pi on 4, which is 7 pi on 4. But you really need to get to a point where you can do that in your head, or you'll struggle here. Okay, next one is at 2 pi plus pi on 4, so that is 8 pi on 4 plus 1 pi on 4, so that is 9 pi on 4. And our final solution is at 4 pi minus pi on 4, 4 pi being 16 pi on 4, take away 1 pi on 4, which would be 15 pi on 4. Again, in this instance, the period of this particular equation is 2 pi. There's been no dilation of the cos function, and so what we should see is if I added 2 pi from pi on 4, I'd get to my next solution at 9 pi on 4. I'm seeing that in the unit circle as well. Pi on 4 plus another 2 pi is just doing an extra lap of the circle. That's taking me out to my second solution at 9 pi on 4. Similarly, 7 pi on 4 plus 2 pi, so plus the period, should get me to 15 pi on 4. 2 pi obviously is 8 pi on 4, 7 pi on 4 plus 8 pi on 4 does indeed get me to 15 pi on 4. Okay, 4 solutions to the equation. So as I said, solution to an equation is a value that when you sub it in makes the equation true. So we should be able to check this. You know, cos of pi on 4 is root 2 on 2, which as you know is the same as 1 on root 2. We could also try cos of 7 pi on 4. Also root 2 on 2. We can try cos of 9 pi on 4. Also root 2 on 2, which is 1 on root 2. Cos of 15 pi on 4. So these are all values that make this equation true. They're all locations in the unit circle where the x-coordinate is 1 on root 2 or root 2 on 2. Okay, let's have a look at another example. We're going to think in degrees for this one, so we just need to switch our thinking a little bit back to degrees. You really won't need to work in degrees very often. There are a couple of questions in this exercise, which is why I include this example here, but realistically, we've moved past degrees and we'll only work in radians when we're dealing with circular functions. Okay, let's go back to our steps. First step is to get the sine or the cos on its own. So in this case, we need to get sine on its own. So we've got 2 times sine of x degrees minus pi on 3 equals 0. So if I add, sorry, not pi on 3, root 3. If I add root 3 to both sides, 2 times sine of x is equal to root 3. Let's divide both sides by 2. Sine of x is equal to root 3 on 2. Okay, so this time we've got sine of an angle is equal to root 3 on 2. So again, we want to think about our exact values. I know the root 3 is in this triangle. Now if I want sine to be equal to root 3 on 2, that means this has to be the opposite side. and this has to be the hypotenuse because sine is opposite of a hypotenuse. And so therefore, if root 3 has to be the opposite side, we must be talking about the angle down here. And that angle is 60 degrees, or pi on 3, okay, because it's half the equilateral triangle. Okay, so all of my solutions are going to be related to pi on 3. Now we want to know, oh sorry, we're dealing in degrees. So pi on 3, it's not pi on 3, it's 60 degrees in this problem. Our answers are going to be in degrees. So 60 degrees. So now we need to think about where our solutions are located in the unit circle. So again, sine is equal to a positive number. The y-coordinate in the unit circle is equal to something positive. So our solutions must be in the first and second quadrants where sine is positive. So angles related to 60 degrees in the first and second quadrants. So 60 degrees up from there, 60 degrees up from there. So that's the location of all of our solutions. Now we want to think about our domain. Okay, so we now want to look at it over a domain from negative 360 degrees to positive 360 degrees. Again, I find it easier to do this in two separate laps. So 0 to 360 is one positive lap, 0 to negative 360, one negative lap. Okay, so let's do the positive first. Let's go from 0 around to 360. Okay, so we get two solutions in the first and second quadrants. Now remember, if we're in degrees, this is 180 degrees around here. So the two positive solutions we get, positive 60 degrees, and 180 minus 60 degrees, that's 120 degrees. Okay, then if we were to go the other way around the circle, so starting at 0 degrees, but going this way, so that's going to be negative 180 degrees, and continuing around to negative 360 degrees. We've got two solutions again, okay, but the first solution is at negative 180 minus another 60. So that is negative 240 degrees. And the next solution is around in the first quadrant again, so that is right round to negative 360, but plus another 60. So that's negative 300 degrees. Again, let's write them in order. Negative 300 degrees, negative 240 degrees, 120 and 60. Sorry, 60 and 120. Okay, as I said, you won't have to work in degrees very often, but it's not asking you here to convert to radians. It's giving you the domain in degrees. You're told to find x in degrees. You just need to work in degrees. Okay, example 5, the last one. Hopefully this will be one where we get a negative value because we haven't really demonstrated that. Okay, so we've got root 2 cos of x plus 1 equals 0. First thing is to get the cos on its own. So let's subtract 1 from both sides of that equation. So it's root 2 times cos of x equals negative 1. And so cos of x is equal to negative 1 on root 2. So again, we need to, first of all, the next step is to think about our reference angle. Forget the negative. Cos is equal to root 2. The negative is about quadrants. Cos is equal to 1 on root 2. Okay, so I know that that's about pi on 4, as I've said to you previously. This is, when I'm working with exact values, I don't usually need to draw this triangle because I know the minute it's got root 2 involved in it, it has to be about pi on 4. Yeah, I don't tend to draw this one, whereas I do draw the 30 degree and 6, or pi on 3 and pi on 6 triangle to differentiate between those. So my reference angle here is pi on 4. All of my solutions are going to be connected to pi on 4. Okay. Then I need to think about quadrants. So this time I can see that cos is equal to negative 1 on root 2. So in my unit circle, the x coordinate is negative. So that means I must be in the second and third quadrants. Okay. Which angles make the x coordinates negative 1 on root 2? Okay. So we're in the second and third quadrants and our angle is pi on 4. So we're going to be here. So I'll get that a bit more accurate. Here and here. Okay, so that is pi on 4 up from there and pi on 4 down from there. So cos is equal to something negative, therefore our solutions are going to be in the quadrants where cosine is negative. But they're going to be connected to pi on 4 because cos is equal to 1 on root 2. Okay, so now we need to think about domain. Okay, this time we're just doing 0 to 2 pi. So that is just one lap of the circle, starting at 0 and lapping around to 2 pi. And we can see that we just get the two solutions in that one lap of the circle. And remembering this is pi here. So my first solution in the second quadrant is pi minus pi on 4. So that is 4 pi on 4 minus 1 pi on 4, so 3 pi on 4. And my next solution is pi plus pi on 4. So that is 4 pi on 4 plus another pi on 4, so 5 pi on 4. So two solutions within that domain. Okay, so the work today is from 14H, or the work right now is from 14H, and that's just dealing with simple trig equations. So by simple, there's nothing happening in here. Every time it was just sine or cos of x equals a number. What we'll look at in the next video is what happens if there's more going on in there, which is going to happen when we're dealing with our graphs, period changes, translations, etc., etc. Okay, but to start with, 14H, get comfortable with the process, with those 4 steps, with recalling your exact values, with thinking about your symmetries, your cast rule in the unit circle, in order to solve the simple trig equations.